In today's lesson, you will be graphing inequalities. This is lesson 2.3.b. Our first objective is to graph inequalities in two variables. Prior to this, you were graphing inequalities in one variable on a number line. Today, we will be using the coordinate plane to graph inequalities with x and y, two variables. We will also determine if coordinate points are solutions to inequalities, and we will look at that both graphically and algebraically. Let's look at some important vocabulary. So here's some essential questions in order to be successful with inequalities. And you may want to, actually I would highly suggest that you write these down in your notes. First thing we have to answer is, what is a boundary line? And a boundary line is just a line that separates the coordinate plane into two parts. It looks just like any other line when you graph a function, only it potentially could be a dashed line, and we'll talk about that in a minute. One thing too about a boundary line is that it separates the plane into coordinate points that are solutions and coordinate points that are not solutions. So what is the difference between graphing an equation and an inequality? Essentially, there is no difference except for two things. Number one is for the style of the line. As we talked about earlier, you will either have a dashed line or you will have a solid line. The second difference is that you will always shade on one half of the coordinate plane. You will shade either above your boundary line or you will shade below your boundary line. And occasionally that could be to the left of your boundary line or to the right of your boundary line if you have a vertical line. So the big question is, when do we use a solid line for the boundary as compared to a dashed line? A solid line is used when the inequality sign is either less than or equal to or greater than or equal to. And the key with these is the or equal to. Remember that if something is or equal to, it includes the number that is listed. So in this case, it would include all the coordinate points on the line. Those would be solutions. Now let's compare that to a dashed line. A dashed line is used when the inequality sign is less than or equal. Okay, notice there isn't, or greater than, not equal. So a dashed line is used when the inequality sign is less than or greater than. There is no equal underneath these. And so remember that when we use these types of signs, the number is not included in the solution. So you do a dashed line to indicate that those points that fall on the line are not solutions. So in this case, only the numbers or the coordinate points above or below are solutions, but nothing on the line is a solution. So let's try some examples. Here's an example. We want to graph and shade the solution area for the following. So example 1 looks just like a linear equation. It's in the form y equals mx plus b, so it should be fairly straightforward to graph. First thing is plot our y-intercept. We want to plot the y-intercept at -5. We know that b, this number on the end, represents our y-intercept. So I'll go ahead and put a point here at the -5. And maybe let's make that a blue point. The next point I will plot with the help of my slope, which is rise over run. So I'm going to go up 2, or I could go down 2, and then I'm going to run over 3, either left or right. So I'm going to go up 2 and over 1, 2, 3 and plot a point. Now I'm going to actually go ahead and plot one more point just so that I get a good line. 1, 2, 1, 2, 3. So I went up 2 and over 3 one more time. When you are graphing inequalities, it's helpful to have a really good accurate line so that you ensure that your solutions are correctly above and correctly below and that you haven't accidentally drawn your line crooked. So I would use a ruler when you're drawing these on your own. Now the final thing is to shade. And actually let's go back. If you'll notice, I drew a solid line. And the reason that I drew a solid line is what we stated earlier. If you'll notice, the example has a less than or equal to. And anytime you have the or equal to with the line underneath, that means that you would have a solid line. Okay, and that means that all the coordinate points on my line are also going to be solutions to this problem. So where do I need to shade, above or below? In this situation, it's easy to look at this and figure it out. We want all the y values that are less than this function, 2/3 x minus 5. Well, if this is my function, then the y values that are less than this function would be below, because the ones above are going to be greater. Notice they go up, they increase, versus the ones below, down here, these are all less than this function. So my solutions are everything represented by the line plus all the coordinate points below the line. Now let's try example number 2. Now this one's a little bit different because it's not quite in slope-intercept form yet. So what I'm going to do is I'm going to put it in slope-intercept form so it's easier to identify where the solutions are. So I am going to isolate y, which means I need to divide all my numbers by 4. Now keep in mind, this is still an inequality, so if I were to have divided by a negative number, I would have had to flip the sign. Except here, I did not divide by a negative number, I divided by positive 4. So 4 divided by 4 is 1y, or just y. And I have y is less than, and here's my slope, negative 5 over 4x plus 4. 16 divided by 4 is 4. So I'm going to graph my y-intercept, and that's up here at 4. And then I'm going to do my slope. Now I'm really careful to note that my slope is negative. So instead of having my line increase from left to right, it needs to decrease or slope down from left to right. So again, it doesn't matter if I count up 1, 2, 3, 4, 5, and over 4, or go down 1, 2, 3, 4, 5. I just need to make sure my line slopes in the right direction. So I'm going to go to the left 4 and put my point here. I'm going to do one more, so I'm going to go down 1, 2, 3, 4, 5, and over 1, 2, 3, 4 right here. Okay, so I want you to think to yourself, what kind of line would I need to draw on this one? A solid line or a dashed line? If you look at the inequality sign, it's less than. It is not equal to, it's not less than or equal to, it's just less than. And as a result, we need a dashed line. One other thing I want you to notice and pay attention to is that I am drawing my boundary line all the way through my graph. That way it splits my graph into two parts. That way it's easier for me to see where the solutions are. So now let's look at this equation as we rewrote it. We want all the y's that are less than this function. Well, again, the y's up here, those are greater. The ones below, those are less than. So that would be the area that I would want to shade, is down here. My solutions to this problem are any of the coordinate points down here in the yellow below my dotted line. Now recognize that none of the points on the dotted line are going to be solutions, but all the points down here in yellow will be. All right, let's move on and try something a little bit different. Oh, actually, let's do one more first, and then we'll try something a little bit different. We'll tackle our third objective after this. This problem is definitely not in slope-intercept form. I can graph it this way by making a table of values, but it would be very difficult to figure out where to shade again. So I'm going to go ahead and put this in our slope-intercept form, so that way when I'm done, I will know exactly where to shade. So I subtract 9x from both sides, and I end up with 3y is greater than negative 9x minus 6. Then I'm going to divide everything by 3 in order to get the 3 away from the y and move it to the other side. 3 divided by 3 gives me 1y. So my final equation will look like this. Y is greater than, and I'm going to go ahead and do negative 9 divided by 3, which comes to negative 3x, minus negative 6 divided by 3 is 2. Now I'm ready to graph this equation. So I will plot my y-intercept first, which is at the negative 2, down here. And then I'll use my slope to help me graph my next point. And again, it's a negative slope, so I'll need to angle downwards from left to right. I'm going to go ahead and go up 3, 1, 2, 3, but that means I then need to go to the left 1 in order to ensure that my line angles the right way. Now I'm going to go down 1, 2, 3, and then to the right 1. You can also think of slope as you need to, if you have a negative slope, it means you have to go in the negative direction at least one way. So if I go in the positive direction for y, I will have to go negative for x. Whereas if I go in the negative direction for y, then I can go positive for x. But as a whole, if you just think of it as angling the correct way, then you'll make sure to have your points and your line drawn correctly. Okay, let's draw our line. See how close I get to my dots. And maybe we can adjust this just a tad. Here we go. And again, notice I drew a dashed line just like the last one. If you look at my inequality here, we have a greater than sign, not a greater than or equal to. So anytime you have just a greater than, you need a dashed line. Let's figure out where to shade. If I look at the equation, I want all the y's that are greater than this function. Here's my function. The line represents my function. The y's that are greater than this are above it, up here. So all those y's are greater than this function. This is where all my solutions rest. Okay, now let's look at our third objective. Our final objective is we want to determine if these points are solutions to the following inequalities. Okay. So in example 4, we have an equation. I can graph it, and then I can see if these points fall in my solution area or not, or I can do it algebraically. And we're going to do it both ways. So let's actually look at it graphically first, since that's what we've been doing. If I plot this, my y-intercept is up here at 7, and my slope is negative 1, 3. So I'm going to go down 1 and over 1, 2, 3. Notice which direction I am going in. Okay, and then I will need a dashed line because, okay, so here's my dashed line, and again I need a dashed line because of my sign. My sign is a less than versus a less than or equal to. Now let's figure out our shading. Our shading needs to be all the values that are less than, or my y values need to be less than this function. Well, here's my function. The y values that are less than the function are all going to be down here. Okay, now let's see where these points fall. So let's mark those. Negative 6, 2 falls right here. That's definitely in my solution area. But 12, 0, well, that's a bad point because that's way out here. Can't really tell. So in this case, I am going to have to look at this algebraically to see if that is a solution. So let's go ahead and plug in 12, 0 into our equation. So let's plug in 12 for x and 0 for y. So we have a 0 is less than negative 1/3. We're going to plug the 12 in for x. And then we have plus 7 on the end. Now all we have to do is simplify and see if this is a true statement. Negative 1/3 times 12 is the same as negative 1/3 times 12 over 1. Negative 1 times 12, it will give us negative 12. 3 times 1 gives us 3. Okay, and now let's simplify a little bit more. Negative 12 divided by 3 is negative 4. And then if we add negative 4 to 7, we get 3. So let's see if this is a true statement. Is 0 less than 3? It is. So this is a true statement. Therefore, 12, 0 is in fact a solution, just like negative 6, 2 is a solution. We found this one algebraically, and we found A graphically. Let's go ahead and look at another one. Okay, in example 5, this problem is not written in slope-intercept form, but we're going to go ahead and graph it using x and y intercepts. We'll get a little practice doing that. And then we'll figure out where to shade based on whether these points are solutions or not solutions. So let's figure out our x-intercept first. And remember that the x-intercept, we plug in a 0 for y. So let's try that. We would have x minus 5 times 0 will be less than or equal to 10. Now let's simplify. 5 times 0 is just 0, so we would be left with x is less than or equal to 10, meaning that our coordinate points for us to graph are going to be, actually let's write that down here so we don't run out of room. That would be 10, 0. All right, let's figure out then our y-intercept. So the y-intercept, if we want to figure out the y-intercept, we would plug a 0 in for x. Okay, so let's go ahead and do that. We will plug in a 0 for x, so we will end up with 0 minus 5 times y is less than or equal to 10. So we're really just solving negative 5y less than or equal to 10. We would divide both sides by a negative 5 in order to move that to the other side and solve for y. And we know that negative 5 divided by negative 5 is just 1. And we will be left with y. And notice we are dividing by a negative. So hopefully right now you are thinking, oh, we need to flip our sign. Always flip the sign if we divide or multiply by a negative. And 10, oops, wrong color. 10 divided by a negative 5 will give us negative 2. Our coordinate points then for our y-intercept will be a 0, negative 2. Okay, so we can plot those. Our first one is over here at 10, 0, and our other one is over down here at 0, negative 2. Now I know that I'm going to draw a solid line because it's a less than or equal to, so I can do that. Okay, and remember that you want to try to draw the line across the whole entire grid so that you have a boundary line. So I'm going to go ahead and extend my line all the way through. Now let's check out these points. Let's do this algebraically and we can see then where we need to shade. So let's actually mark this point first. This is at 15, negative 1. Again, that's off the graph. It'll be very difficult to mark that one. So let's mark the second one, negative 7, negative 6. So I would go out here to negative 7, and then I would drop down here to negative 6. And I'll go ahead and I will place a red dot there so that we remember where that is, right here. And then let's go ahead and test that point algebraically since it sits on our graph. Okay, let's go ahead and plug in a negative 7 for x. We would have a negative 7 minus 5 times negative 6, plugged in the negative 6 for y, is less than or equal to 10. Now all we have to do is simplify and see if this is a true or false statement. A negative 5 times a negative 6 will leave us with a positive 30. Remember, do your multiplication first, order of operations. Now we can then subtract. A negative 7 plus 30 gives us a positive 23 is less than or equal to 10. Is that a true statement or a false statement? That is most definitely false. So what does that tell us? That tells us that this point is not a solution. So if we're trying to figure out which half our solutions lie, we know that they would not be below. Our solutions would then have to be above. Okay. That's where our solutions are. Now finally, in order to figure out if 15, negative 1 was a solution, we could just plug it into the equation and figure that out, just like we did for b, -7, -6. Or we can look at our graph and get an idea of where that point would lie. Because the line is growing, right here is our x-intercept. That means the line will be above the x-axis from here on out. This point, 15, -1, is going to be below the line, so this point will not be a solution. And that concludes our lesson for today. So let's just make sure that we are clear on what we went over. We graphed inequalities in two variables. We learned about boundary lines and how to shade. And then we finally determined if coordinate points are solutions to inequalities. And we looked at that both graphically and algebraically.